Hello everyone, welcome to the new session of the End-to-End VoLTE Training Campaign. In today's video, we're going to go through the VoLTE key actions, including the main features and also the parameters, which can be done to improve the VoLTE performance. We'll cover firstly the high-level view of the key features and actions which can be done in the network. Then we'll try to go through one by one, especially for the VoLTE features part, which is more related into RAN part. So let's move forward and see what we have. So actually this figure or mind map is summarizing like some of, or say, let's say the VoLTE main key actions. As you can see here, I split this one into 4 categories. In general, usually when you optimize VoLTE networks, you will just look into features or actions or features in general, which can improve coverage and robustness, okay? Then you have the mobility management, where you can improve, for example, the network performance through improving the layering strategy, and you have different features. Then we have some specific parameter tunings, including whatever mentioned here, as for example, tuning the maximum HARQ retransmission. Then you have some actions which is more related into end-to-end view, which can improve the VoLTE call setup time delay. So our main focus actually would be in the first area, which is related to the main features in the VoLTE. So in today's video, we're going to cover the first two parts, which is related to TTI bundling and robust header compression. And the main important point that I will be covering those two parts also from using the logs, just to show you how to verify the feature functionality and how this kind of feature you can confirm how this kind of feature is working from the logs or not. So let's move forward and see what we have. Actually, before I jump into the details of the two main features which we are going to cover today, I just would like to let you understand. Usually, any feature tuning will rely or would depend on this kind of box, which is related to the what kind of inputs is being reported to the input B and or being configured within the input B and or the BTS, and what the input B do and what kind of resource will be allocated. So if you look into this box, you'll find that you have different inputs. I'll just give some of them here, which is, for example, UE related inputs related to the UE capability, measurement gaps, and the synchronization stats and so on. Then you have this kind of HARQ feedback, which is, for example, the user replying for its acknowledgement or non-acknowledgement, and this can have some configuration from the NLP, for example, to increase the number of non-acknowledgement trial or retransmission trial, which can be done from either in downlink or uplink. Same, you have the NLP will differentiate between the surfaces, for example, using the XCI. For example, XCI1 will have a different budget delay or bucket budget delay compared to, for example, XCI9 or 5 or 8 or even 5. So as overall quality of service parameters, not only for the packet delay, I mean. And also you have this kind of channel input CSI, which is being reported just to indicate to input B what kind of radio condition of these users is being now, for example, what is the CQI channel quality indicator and so on. So the input B can start selecting his MCS selection and so on. And you have also the downlink power configuration. For example, you can have the reference signal power, you can increase it, decrease it, you can have some optimization in BDCH power, you can increase it, reduce it. Then you have the transmission mode, whether you are going to use closed loop, open loop, and so on. All these kind of inputs, the input B will take these inputs and we'll try to make the calculation for the scheduling calculations and to check what kind of priority, for example, which users having highest priority for in terms of scheduling compared to the others, start to, based on these inputs, selecting the MCH and so on. Then it will decide which user is being selected for the scheduling and resource blocks, for example, which being allocated for user and MCS. Why I'm using this part? Usually any features or even parameters or even any optimization actions, if you understand this box very well, you will be able to know what you can do. For example, if you would like to increase the robustness, you can increase, for example, the number of HARQ retransmission, but still this is, you need to understand that is, for example, can increase retransmission resources. So you need to be very careful whenever you optimize this kind of things. But any action can be done here. It can having improvement or even degradation on your inputs. So just like you need to understand that in general, VoLTE is, or even 4G or 5G, is more about link adaptation. How the input is doing link adaptation based on the inputs you are giving or even configuration. So again, all the feature will be playing in this inputs here, in order to optimize and get a good results as a scheduling results for the user. So let's move forward and see what we have for the two features. So the first feature we're going to cover is related to TTI bundling. As you know, this TTI bundling is, you can say it's now becomes like standard features, as is almost enabled by default for any vendor or even operator, and it's like mandatory, one of the mandatory features that must be enabled. But in today's session, I'm try to cover it from different perspective. Also, I would like to add one additional point related to something called advanced TTI bundling, which is need some optimization, sometimes need some to be enabled for some vendors and so on. And also you need just to understand how this kind of advanced TTI bundle is working. So initially let me explain how TTI bundling in general is working. In the normal case scenario, if you look into that part here in the left, in the normal scheduling scenario, the resources will be scheduled right in 1 millisecond. So all the data will be sent, for example, within particular TTI from the unit B, the UE in terms of uplink to the unit B will be transmitted in this particular TTI. But once the unit B trigger TTI bundling, and in general how TTI bundling is being triggered, TTI bundling actually is being based on uplink SNR, PUCH SNR. So for example, if this uplink SNR is falling below a certain configured threshold, let's assume that the threshold of the SNR is 10 dB, and now the user is having 7 or 6 dB or whatever. So the unit B will decide that this user should enter the TTI bundling state because it will assume that this user having a bad radio condition. So the NLP would like the users to enter the TTI bundling state in order to get a better performance in terms of uplink. How this can be done? The NLP will send RRC configuration message to the user, asking him, now you are in TTI bundling state, so now you can start using the scheduling of the TTI bundling. So in general, how the scheduling TTI bundling is being done, as you can see in the figure, assuming now that before in the normal scheduling, the user was transmitting one for example, transport block here. Now this one will be retransmitted or being sent by the users. Like the same data will be sent 4 times in 4 consecutive TTIs as shown here, but with different redundancy version. But the same data will be transmitted. Accordingly, this will be reflecting in the decoding process from the NLP side. Will be like a diversity, so that you will have higher energy per bit, per bit. So that this means you are improving your uplink coverage because you have a better decoding from the NLP side because you are sending 4 different data in 4 consecutive TTIs. Sorry, same data in 4 consecutive TTIs with different redundancy version. So this will improve the redundancy performance and will result in higher energy per bit. So can improve the uplink coverage by around 2 to 3 dB. Now, the idea here, as you can see for the acknowledgement part, it will be sent after 4 milliseconds from the last transport clock being set. For example, here you need to count 1, 2, 3, 4. So will be like, you assume from the first packet till the last, it should be around 8 milliseconds. While in the normal scheduling, it will be sent here for the acknowledgement. So you can assume it as one of, it can increase the delay a little bit, but usually the TTI bundling is more triggered for the very bad users, especially or edge user for the uplink. So this will have a good performance. The second and the most important part as well, now we explain that in terms of coverage, you will have a higher energy per bit, so it will improve your uplink path loss uplink coverage by around 2 to 3 dB, sometimes up to 4 dB. But still, you have also some capacity gain. How this kind of capacity gain you can observe this capacity gain based on TTI bundling. In case of without TTI bundling, if the user is already in the edge coverage and he having a very poor performance on the uplink, so in this case he will need to have this kind of RLC segmentation. He is having he have less energy now or have less power because he cannot send the complete packet in one time because he have limited uplink coverage. So the user will the RLC layer will do the segmentation into, for example, as you can see here, four buckets. For example, instead of 1, it will be sent in 4. And the idea and it will be sent in 4, as you can see, in 4 transport block. Each one will be sent in different TTI, but this different data is being split. Why here the splitting is being done? The splitting is being done to increase the power per bit or per resource block. So you will have a much better coverage whenever you do a segmentation. But also the segmentation is increasing or decreasing the capacity because for each one of those you will require a BDCH allocation, right? Then it be which TTI or which he can send this particular data. So you need a 4 BDCH allocations, and also for each one of those you will write your UE will require to send acknowledgement for each of those packets which being sent in the TTI. So this is also increasing the HARQ feedback. Instead of one HARQ feedback, you have HARQ feedback. But in case if the TTI bundling is being triggered and the input be already instructed the UE to enter the TTI bundling state, what will happen? In this case, the user know that there is a better performance or better decoding and even having higher energy per bit. So because he's in TTI bundling state, so he will send a complete RLC. For example, it was SDU, BDU. It will send the same one without without any segmentation. So this will result again in sending this same TB, but only transport clock and for TTIs. So this one would result in less BDCH allocation. So it can have improvement in your BDCH allocation in case of the segmentation point of view, and also will have one HARQ feedback because for those four TTI, for those four transmitted data, then same data and four consecutive TTI, it only require one HARQ feedback. So in this case, you will have a better performance in terms of improving capacity because you will not have any RLC segmentation anymore. And also one of the things that can be triggered out of the TTI bundling, whenever the users enter the TTI bundling state, he will be out of the DRX. He will exit DRX directly, so he will not be in DRX anymore. So this also can have some reflection even in latency or even in the quality point of view. So this is the three main gain of the TTI bundling. And just a side note, usually the TTI bundling is supported by FDD. It can be supported by TDD in very specific cases and depend on the, as mentioned here in below comment, depend on the subframe configuration. Usually we use this sub configuration 2, which is SA2, which is called subframe assignment, which is as a location, it's 622, means 6 for downlink, 2 for uplink and 2 for uplink. 6 for downlink and 2 for uplink. And 2 can be guard band or can be like having a dynamic between uplink and downlink. And the idea that usually that the TTI bundling require a 4 TTIs for uplink, right? That's why you will have a limitation TTI bundling. That's why it's only being supported by this kind of configuration with 0, 1, and 6. But usually those kind of configuration is not being used. Usually use the subframe configuration 2, and also doesn't work with the semi-persistent scheduling for the same U. So this is just an extra comment. Now let's move forward to see how can you verify the TTI bundling from the UE logs. And secondly, what it means by advanced TTI bundling. Before going to the advanced TTI bundling or how to verify in general TTI bundling from the DT logs, I would like to just recall one point. One of the limitations of the TTI bundling, once the TTI bundling state is being triggered, you will see if you read this, if you quoted this from 3GPP, we can see that if the parameter of TTI bundling provided by high layers is set to true, means TTI bundling is being triggered, then the modulation order MCS will be set to 2, and this is will be like QBSK, which means you have only 2 bits can be transmitted in the uplink, and the resource blocks will be limited to maximum 3 resource blocks. So in this case, what it means, but once the bundling is being triggered, so assume that the user is doing a VoLTE call and he have uplink data or you need to do something on uplink, so your uplink data will be very limited in this case of the TTI bundling. So this was using the TTI bundling, this was causing a limitation uplink through. But now after the release, starting from release 12 upwards, the 3GPP like introduced this capability for the devices, which is if the if the user is the user to release 12 and he will be supporting this like in the capability, you can check this kind of information, which is called no resource restriction for TTI bundling release 12. This means that you support TTI bundling regulation without resource allocation restriction. This kind of resource blocks will not be any more applicable for those release 12 users. And usually we call this as advanced TTI bundling. And also there is one additional functionality which can be done. Here is called enhanced HARQ pattern FDD release 12. This means that here for the you support something called enhanced HARQ pattern for TTI bundling operation for FDD. Usually that in case of retransmission in the normal TTI bundle, it requires 60 milliseconds for the normal users to make the retransmission. But in case of the enhanced HARQ, it will only require 12 milliseconds. So this can be reflected also in latency improvement. And I will show you an example from the logs how to verify and how to check this kind of capability and how to check whether advanced or enhanced HARQ is being enabled or not. So let's see. So here we'll just check how advanced TTI bundling or TTI bundling general is to confirm from logs whether it's being activated or not. And the second point that will explain what it means by enhanced HARQ pattern release, and we'll check also how to confirm the logs. The first two commands here is just quoted from 3GPP document, which I just showed you in the previous slide. So initially what will happen, if the first of all, the init B will check whether the user is achieving the TTI bundling condition, which is again based on the user's uplink radio condition, which is SINR. So assume that he's not achieving, so he will not be triggered. So the init B will decide that this user is not a candidate for TTI bundling, so no TTI bundling will be triggered. But instead, in case of the TTI bundling is being triggered, then the init B will check the capability of this user, whether he's supporting this enhanced HARQ pattern release 12 or not. If it's not supporting, then the users will use the old process, which is read to the binary release. So the HARQ RTT is 60 milliseconds, as I mentioned, and the maximum uplink BRBs will be limited to 3. So those particular users, and even if the feature is not being enabled, will having a limitation in even uplink, and will having kind of latency increase. So this is kind of the drawback. But in case if the capability is being supported and this feature is, or this parameter is being enabled, and this is, you need to check with your vendor, maybe they have a different perspective, but this is just from 3GPP. If it's being enabled, so that the bundling, this means the bundling release 12 is being supported, so the HARQ RTT will reduce from 16 to 12 milliseconds, and now you can get even more than 3 resource blocks for the uplink allocation. And in the right figure, this is how to confirm in general how TTI bundling is, whether TTI is being triggered or not. First thing you need to check under the ROHC configuration message will be sent from the init B to the UE. Under this ROHC configuration message, you will find something called radio resource configuration dedicated, as shown here. Under that, you need to check the MAC parameters, which is MAC main configuration. You'll find if it's being triggered, this one will be true. If TTI bundling in general is not being triggered, this one will be false. This is for the normal HARQ. But in case of enhanced HARQ, as you can see here, also it will be the same. If the user supporting is fine after MAC, under MAC configuration V1020, we'll find that there is additional something called HARQ pattern release 12 is being supported, and this is indicate that the user now is falling under this category, so he even can have a better latency and has no limitation anymore in the uplink resource block allocation. So this can also give a better performance in terms of uplink through. And this is all what I need to discuss about TTI bundling. Now let's move forward for the second feature, which is robust header compression. Okay, now it's about robust header compression. This is also a standard feature which is usually enabled by default. You just need to check or make an audit for your network, but usually this is being enabled. But let's just explain how this feature is working and what kind of improvement we can get whenever we enable this feature, and how also to verify from the drive test whether the feature is being enabled or supported by the users or not. Okay, as if you can recall, robust header compression in general, what it do, as mentioned by the name, as stated by the name, it just make a header compression. So the main advantage of this feature is trying to reduce or make a header compression to reduce in general the packet size. And if you reduce the packet size, you will be able even to improve your uplink performance or block error rate, because you will have, for example, assume you're using 20 resource blocks on uplink allocation, but after the packet reduction, size reduction, you need also to only to use 10 resource blocks instead of 20. So you'll have even more power per resource element. So this will be reflected in you having a better uplink coverage and even less block error rate, or much better block error rate. So the main advantage here, you are improving the capacity in general because you are doing a reduction for the packet size, and you're improving your uplink performance, especially for block error rate and coverage as well. So this is actually the general idea in the left here. If you look into the left as a general high level concept, you see, for example, this is the compressor and this is the decompressor, even sender or receiver. So in the compressor, what's happening in the first, when the packet is being transmitted, as you can see, you have the data or the payload, and you have some here additional header, which is IB header, UDP header, and RTB header. And usually the IB header is having very high size. So actually, the main idea that I would like to confirm that this is happening at the PDCP layer. This is the robust header compression is happening at the PDCP layer. So at the PDCP layer, you will be having a compressor. The compressor will establish the context. I will explain this one in more details. Then it will be transmitted. The compressor and the compressor will have an establishment of the context through sending the first packet in general as it is, without any compression. The first packet will be sent from the compressor to the decompressor or sender to receiver. Without the first packet will send without any compressor, but both of them will establish a context out of this packet. For example, this packet have a specific sequence. If you can see here, this packet, for example, is 21XX01. So we found that there is some static numbers within the packets. This is all the packets. It's 21XX01, 21XX02, and till 06. And that the compressor will understand that the context of this one is 21XX0. So they will establish the context, which is, as you can see, between the compressor and the compressor. The first one will be sent as it is. Then they will establish the context, which is 21x00, as highlighted here. Once the context is being established, now only the one which is out of the context will be transferred. So before you used to transfer, let's assume this one as 6 bits or 6 bytes, for example, 1, 2, 3, 4, 5, 5, 6. Now we need only the compressor need only to pass only one packet, and the decompressor, because it's having the context being established, can decode the data successfully. So in this case, usually instead of, or initially you would like to send, for example, 6, let's say bytes, multiply by 6 also, which is 6 numbers here, you will have 36. So once you establish the context, you need only to transfer 11. 11, why it's 11? Because the first one you need to transmit as it is, which is related to 6, then 7, which is the last digit, 8, 9, 10, 11. So you have 11. Then you need just the compression ratio will be around 70%, because usually you need to transmit 36, but in this case you are transmitting only 11 instead of 36. You have around 70% improvement or reduction in the packet size, and this is how it's been working. And as you can see here, usually this is what happens after the header compression. For example, here you have the larger size of the header is related to IP version 4 or IP version 6. IP version 6 even having higher packets. So usually the robust header compression will reduce it to around 1 to 3 bytes. And if I can recall it, usually IP version 4 have around 40 bytes as a size, and IP version 6 will be have around 60 bytes. So at the end, it will reduce to only 1 or 3 bytes, and this is how we get the gain. So now let's jump into how to verify first the capability of the device from the logs, and what kind of requirements, which parameters we need to check from the logs, from the capability, and how also to confirm whether it's being triggered by the InnoDB or not. Okay, if you look into this figure, this is actually the figure on the left here. This is if you look into that part under the UE capability information message, which is sent by the UE to the InnoDB. The UE is informing the InnoDB about its own capability. So you need to go through under the BDCP parameters. As you mentioned, that ROHC or ROHC is supported by the BDCP layer. So the user is sending something called profile 1, 2, 3, 4, 6, and so on. Actually, usually the voice or the robust header compression for the voice is about profile 1 and 2 and even 3, but those or especially 1 and 2. So you need just to check whether those being supported or not. If it's false, this means this particular user is not supporting the robust header compression, because you need support profile 1, 2, and 3 as shown here. So this is the most important from the capability point of view. So you might do some insights in the network to check, for example, how many users supporting the feature or not. Then we can, for example, raise it to the vendors to try to ask them if some device is not supporting, to ask them to try to add the capability for the devices. And here from the InnoDB side, whether during the ROHC configuration when sending XI1, ROHC configuration to configure XI1 data radio bearer, it will send under BDCP configuration data, again ROHC in the BDCP layer. So if it's sent not used, this means header compression is not being activated. The feature may be off, not be working. So this means it's not being or even the user not supporting. But if it's being activated, as you can see here, it will send under the same part here, BDCP layer, under the BDCP configuration. Here, for example, first the RLC, as you know that for XI1, it's usually using unacknowledged mode. And here this is the ROHC configuration. So it will send profile 1 and profile 2, which is showing as true here, which is indicating that yes, robust header compression is being supported. So now we can start establishing our context. And that's it for today's session about the first 2 features. Stay tuned for the remaining features. And if you like the session, please press like and comment, and please share it with your friends and spread the word. Thank you very much, and see you next session.